Welcome to this explainer. Today, we are diving straight into a cosmic detective story to unpack literally the most violent, mind-bending explosions in the entire universe. We're talking about events so unbelievably powerful, they briefly outshine the rest of the universe combined. We are looking at gamma-ray bursts, or GRBs. Now, if you follow high-energy astrophysics, you know these transients have completely revolutionized our understanding of stellar death and the very limits of physics. But when we actually map out the mechanics today, the sheer scale of these cataclysms is it's breathtaking.
Section 1. The brightest of all time.
To really wrap our heads around the extreme nature of these phenomena, we've got to start with a recent event that just completely shattered our existing models. Back in October 2022, a signal reached Earth that was so intensely powerful, it temporarily blinded our space instruments. Astronomers designated it GRB 221009A. Okay, let's dive into this. 1.2 times 10 to the 55th ergs. That is the estimated isotropic equivalent energy released by this single burst. To put that absolutely staggering number into perspective, this event released more energy in just a matter of seconds than our sun will emit over its entire 10 billion year lifespan. It's an outpouring of energy that fundamentally tests the limits of what we thought was possible in astrophysics.
Astrophysicist Dan Perley perfectly grounds this math in sheer awe. He stated, "There is nothing in human experience that comes anywhere remotely close to such an outpouring of energy. Nothing." And he's completely right. This wasn't just a bright flash. The LHASO observatory actually recorded photons from this burst hitting an unprecedented 18 tera-electron volts. So we're talking about individual particles of light carrying macroscopic amounts of kinetic energy, literally punching through the cosmos just to reach our detectors.
The astronomy community literally ran out of superlatives for this one, officially dubbing this burst the BOAT, the brightest of all time. At its peak, it delivered over 6 million gamma-ray photons per second. What's especially wild is that the radiation wave was so immense it was detected by spacecraft that weren't even designed to look for gamma rays. The Voyager 1 probe, way out in interstellar space, caught it. Even various orbiters circling Mars detected it. It was that massive.
Section 2. A Cold War Cosmic Mystery.
But before we were measuring tera-electron volts and blinding modern satellites, the very existence of these explosions was actually a closely guarded military secret. The discovery of GRBs is, honestly, one of the greatest accidents in astronomical history. Back in 1967, during the Cold War, the U.S. military launched the Vela satellites. Their job was to monitor Earth for atmospheric nuclear detonations to enforce the Partial Nuclear Test Ban Treaty. Well, instead of finding Soviet tests, they found these intense flashes of gamma radiation coming from deep space. Total surprise. It wasn't until 1997 that the Italian-Dutch Bepo-SAC satellite finally detected a fading X-ray afterglow, which let us pinpoint a host galaxy. And then, jumping forward to 2017, we officially entered the era of multi-messenger astronomy with the GW 170817 event.
Section 3. Collapsars and cosmic crashes.
So what is actually causing these massive spikes in gamma radiation? For decades, astrophysicists debated what the progenitors could be. But as the data piled up, a clear split emerged. Now, what's really interesting about this is how neatly the universe divides these events, revealing two distinct paths to cosmic destruction. On one hand, we have long GRBs. These last anywhere from 2 seconds to several minutes, and they happen when a massive, rapidly rotating star exhausts its nuclear fuel and its core collapses into a black hole, a process we call a collapsar. On the other hand, we have short GRBs. These last less than 2 seconds, and they're caused by something entirely different, the incredibly violent merger of two ultra-dense compact objects, like a pair of neutron stars spiraling right into one another.
But, of course, the universe always loves an exception. Recently, astronomers identified a super-rare subclass, ultra-long GRBs. We're talking bursts lasting over 10,000 seconds. A prime example of this is GRB 111209A, which lasted for over 3 hours. Research shows that instead of forming a black hole, the collapse of this particular massive star gave birth to a magnetar. That is a highly magnetized, rapidly spinning neutron star that acts like a central engine, just continuously pumping energy into the burst and stretching its duration to absolute extremes.
Section 4. Afterglows and relativistic jets.
To understand why these explosions are visible across billions of light years, we really need to look at the anatomy of the blast itself. The physics here are almost beyond comprehension, but breaking it down makes it pretty clear. So, the crucial point is that a GRB is not just a sphere of exploding gas. Whether it's a collapsing star or a neutron-star merger, that newly formed central engine, usually a black hole, funnels the chaotic material into a highly focused, tightly collimated beam. These are relativistic jets. They literally punch right through the surrounding stellar material at near the speed of light. And if, and only if, that focused jet happens to be pointed straight down our line of sight toward Earth, we see that blinding prompt flash of gamma rays. It's kind of like a giant cosmic flashlight pointing right at us. But that prompt gamma ray flash, that's really just the opening act. As that relativistic jet slams into the surrounding interstellar gas and dust, it creates this massive shockwave. The jet decelerates, and all that kinetic energy gets converted into a prolonged, fading emission that we call the afterglow. This is the exact mechanism that the Beppo-Sachs satellite finally managed to capture back in 1997, which gave us the smoke and gun we desperately needed to understand how these events actually work.
And this brilliantly illustrates exactly how we study that fading afterglow today. As the shockwave cools down and slows, the radiation it emits shifts across the electromagnetic spectrum. It steps down from X-rays to ultraviolet to the optical light we can actually see, and eventually stretches all the way out into radio waves over weeks or even months. Catching this multi-wavelength fade across the spectrum is exactly what allowed astronomers to measure the redshifts of these host galaxies. That proved, once and for all, that GRBs happen at tremendous cosmological distances.
Section 5. Multi-messenger astronomy in action. Let's move on and see how this all builds together. Because we are no longer just looking at light. We're now combining different types of cosmic signals to solve these astrophysical puzzles in real time. This modern era of multi-messenger astronomy has completely transformed our understanding of short GRBs. In 2017, the LIGO and Virgo observatories physically felt the ripples in spacetime, gravitational waves, from two neutron stars colliding. And then, just 1.7 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from that exact same location. This was the legendary GW 170817 event. Catching both gravitational waves and electromagnetic radiation from the exact same merger, it literally revolutionized astronomy overnight, proving the origin of short GRBs definitively.
Today we rely on a highly sophisticated, coordinated network to catch these fleeting events. We've got a whole fleet of space and ground-based observatories up and running. NASA's SWIFT, the Fermi Space Telescope, ESA's Integral, the high-altitude LHASO Observatory, and the newly launched Einstein probe. When a burst goes off, these instruments actually talk to each other. They automatically slew around to catch the prompt emission and track that afterglow across all those different wavelengths we just talked about.
Section 6. Lighthouses and Unsolved Mysteries.
As our instruments get better and better, we're pushing further back in time and naturally uncovering new questions. When we look at the cosmic record breakers, the extremes are just staggering. We already talked about the boat taking the energy record and that ultra-long GRB 111209A. But consider GRB 090429b at a redshift of 9.4. That means this explosion happened over 13 billion years ago, back when the universe was just a tiny fraction of its current age. Because they are so incredibly bright, GRBs act as standard candles. They're like cosmic lighthouses, allowing us to peer back and study the very first generations of stars that ignited in the early universe.
Now obviously, with that immense brightness comes some immense danger. The power of these jets is so extreme that if a GRB went off within our own galactic neighborhood, and that relativistic jet happened to be pointed directly at Earth, it would be devastating. Even from light years away, a direct hit could completely strip away our ozone layer, exposing the entire planet to lethal ultraviolet radiation from our own sun and triggering a mass extinction. Fortunately for us, these events are incredibly rare, especially in our older, mature corner of the Milky Way. So no need to panic just yet.
But while we don't have to worry too much about our immediate safety, physicists do have to worry about the math not entirely adding up. And this brings us to a major unsolved mystery, the baryon loading problem. You see, for a GRB jet to reach near the speed of light, it has to be incredibly clean. If the jet scoops up too much surrounding heavy mass, too many protons and neutrons, which are known as baryons, it's going to get bogged down and slow into just a non-relativistic wind. So how on earth does the central engine manage to punch a perfectly clean jet through a dense, collapsing star or a messy neutron-star merger without losing its speed? That remains heavily debated. In fact, because of this exact baryon-loading problem, some astrophysicists are proposing entirely new paradigms. For example, researchers Sivaram and Arun have proposed a really fascinating alternative model. They suggest that some short GRBs might not be neutron star mergers at all, but rather the collision and annihilation of gravitationally bound objects made entirely of pure dark matter particles. Because dark matter doesn't contain baryons, boom, there's no baryon-loading problem to solve. Now, it is important to note this is an alternative theoretical scenario we're looking at here, not established fact, but it brilliantly illustrates how GRBs are constantly pushing us to test the very limits of our physical frameworks.
And that leaves us right here. From Cold War anomalies to massive multi-messenger milestones, gamma-ray bursts remain the most energetic extreme laboratories in existence. As next-generation telescopes come online, we really have to ask, could these fleeting flashes of gamma radiation ultimately be the key to unlocking the dark ages of our universe? Could they reveal exactly how the first stars lived, how they died, and how black holes are truly born? It is a staggering thought to leave you with today. Thank you so much for exploring this with me, and keep looking up.